are not allowed. For example, if I have runs of 0, it has to be of certain length between, let's say, d and chi, between 2 and 5. I have to either have 2, 0, 3, 0, 4, 0, 5, but not 6. The capacity of such a channel is unknown. I think we know why it is unknown, and I think we actually know what's going on. And the problem is very difficult. It reduces to top Laplace exponent, the random matrices, and many, many things here. But this is, here we have some bounds, we know very little, and we would like actually to understand how much information we can send in such a system, which I believe will contribute to diversity, biodiversity. Distributed information I already mentioned to you, so I don't understand what is the difference between one bit here and one bit somewhere there. Until it comes to me, is the time required to deliver this bit to me should be somehow involved in the definition of information? No, I don't know. Speed of information, I told you that maybe speed of actual information is propagated with speed of sound, not light, and here is light. Take wireless computing, that is not my model, it's my colleague model, Philip Jacquet. Imagine that when you have your users that are connected components, they do not touch each other. With the connected component, you can deliver a message very fast with the times light of speed. But when you have disconnected components, when you want to send information from this user to this user, in order to do it, this connected component will move slowly. And when they touch each other, then you can deliver a message. So what you need, you have movement of clusters, and whenever they touch each other, you send information to the other cluster, connected component, and you have to wait until you can deliver something from here to here. This actually reminds me of the situation in which sound is spread out in water, because my understanding is what happened, water molecules, the way the sound was spread, you actually they have to touch into each other in order to transmit sound. So actually, you can mathematically prove that in this example, speed of information is much closer, actually equal, if we agree on certain definition, to the speed of sound. Structure, we know very little, and we know that in gene networks and in shape of molecules, in chemistry, we don't know how to measure structure. This is, I think, one of the most important aspects that we have to go forward. The other thing which is related probably to this audience, security, suspicious activity, is my Gatalak. We discussed this recently, and actually Mike came up with a very nice model. And the idea is the following. Okay, we have massive data, whether it is DNA, or it is locked-in file, or whether it is KMI data, or Walmart data, whatever it is, or bank data. There are some relevant information to your query. And actually, think about Google, okay? When you do a query, you will receive a lot of junk and very little information. So actually, this massive data situation was happening. You want to get relevant, useful information, and probably certain subset of symbols of whatever you deal with will help you to extract this information, and all the others symbols are actually have to be treated as noise. The problem that I cannot dig out information from the protein database is because it is too big, and most of the thing is completely irrelevant to my query. So how can you filter out somehow, and how we define, in this case, what is information and what is not? And this is relevant for the definition of information within the context of massive data. We don't know yet how to do it, but at least we have one model that might help us to understand it a little better and probably to do something. Okay, Physics of information. Physicists actually thought about this, and entropy was not introduced by Shannon, as you know. It was introduced by Boltzmann. Boltzmann entropy for gas, let's say, was denoted by S, let's say, is log of the number of states, number of macrostates for molecules. Bigger W is, the bigger it is, the bigger S is. K is just a unit constant, we don't care. So why Shannon actually used the same name? Actually, Shannon didn't know how to call his function, and he asked from Neumann, probably one of the greatest or the fastest mathematicians of the 20th century. And for one, I told him, call it entropy because nobody understands what it is. And in a sense, he was right and introduced a lot of confusions. But we'll see that actually Boltzmann entropy and Shannon entropy are the same within the context. So Boltzmann wanted to find out how molecules are distributed within a container of a given capacity. And let's follow his thought a little bit. So let's assume that I have n molecules within a given space. And let's assume that every molecule, so I divide this space into small cells of size n. And within this cell is very small. So within this cell, I do not care how the molecules are distributed, and the energy is more or less fixed. So I have total number of molecules in n, total energy is E, on how many ways I can distribute this molecule within this n cell. So if I would allow to permute molecules within a cell, it would be n factorial. But I'm telling you that the cells are so small that any permutation within the cell is irrelevant. So I have to divide by n1 factorial, n2 factorial, and n factorial, with n sub I the number of molecules within a cell. Okay, we assume for simplicity that energy within the cell is set. So what Boltzmann asked, which distribution is most likely to occur within such a simple model? And his answer was, the distribution that will occur is the one that make W as big as possible. So let's try to do it. Let's follow Boltzmann. So let's compute W asymptotically, of course. I take log W, I apply the Stirling formula. And after some manipulation, I will get this one, which is nothing else, as the entropy, except that this is an optimization problem, max this, subject to this. It turns out that the best solution is when within a cell you have the same number of molecules, so uniformly distributed. In fact, when you take Shannon entropy and you maximize it, is maximized when the distribution is uniform. And that's what we are getting again. So in a sense, Boltzmann entropy is a Shannon entropy that maximizes the number of all possible ways in which molecules can distribute. You probably heard about second law of thermodynamics, which tells us that that entropy cannot decrease. So if I take this bottle, if it is and I fold it, okay, let me take something else so that it can break, then the entropy, let's say, of a cup, before I break it, is much smaller when it folds and breaks up. Why? Because the description, remember, entropy is related to description. The description of a cup is relatively simple, but it's much harder when it breaks into many pieces. So the complexity description is much more complicated, so the entropy increases. And that is more or less second law of thermodynamics. But Maxwell came up with a very interesting thought experiment. He said the following. I have a container, and I have a demon who has a trap, or a door. And what this demon does, it looks at the molecule, and those molecules that are very fast, it lets it go to the left side, so it will be much hotter here than here. But if you do it in a bath of constant